Broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Welcome to this webinar. This is Maggie Ortiz, Milan Program Manager at EERI. And before we get started, we just want to go over some basic GoToWebinar controls. Gilberto, if you could go to the next slide. This slide shows a screenshot of the attendee control panel, and you can click on the orange arrow to expand it, open or close the control panel. And this is also where you can ask questions of the presenters by typing them into the question pane and clicking send. If time permits, we'll have a little bit of time for questions after each speaker. So if you have any questions for a specific presenter, please send them in as that speaker is talking. Now I'll go ahead and turn it over to Gilberto Mosqueda from UC San Diego, who will be moderating this webinar.
Hello, everyone, and thank you for joining this live webinar organized by EERI. My name is Gilberto Mosqueda, and I'm one of the reconnaissance co-leads for the Mexico earthquake as part of the EERI reconnaissance efforts. And I just want to quickly highlight a few of the activities that EERI has been involved in following the September 19th event. Including a virtual clearinghouse that has been set up for information. In addition to the webinars that we had, there's a resource library, data map, photo gallery that you can look into for more information. EERI served a key role in coordinating 20 international U.S. reconnaissance teams through coordination calls and field team meetings where we all were able to find out where other teams were right out the field, any interesting sites to see. So that was, I think, a significant effort in coordinating a lot of the teams that were deployed immediately following the event. They also deployed a team focused on the earthquake early warning system and planning events like this webinar, as well as some conference presentations, including a session planned for the national conference coming up in June. We're also working with SMIS on planning a joint report with our colleagues in Mexico. And I just want to quickly also thank all the universities, government agencies, practitioners, and all the individuals that really helped realize these reconnaissance efforts for EERI team members as well as others following the earthquake. Just quickly show the virtual earthquake clearinghouse. If you're interested in more information on this earthquake, this site here has a data map, reconnaissance photo gallery. You see a link to the right, for example, on the past webinar we had a few weeks following the earthquake, as well as links to other reports in the resource subsection of this website. So you're welcome to explore it and find more information on this earthquake. Today we have a 2-hour webinar with 6 speakers. We're hoping to have about a 15-minute presentation by each speaker, followed by questions. So feel free to type in some questions as we go through the various presentations. We'll start with Marty Hudson from working with the SEAOSC team and also from Wood PLC on ground response overview and foundation failures of pile-supported buildings. Then we'll look at a behavior of a prototypical concrete frame building by Ezra Jampole from Exponent. We'll look at a specific building, Oaxaca 80, by Prateek Shah from Purdue University. Building performance in Mexico City by Jennifer Land from GMS, working with the ATC group. We'll have a presentation on bridges by Mark Yashinsky from Caltrans, and impact to water and power by John Eidinger from G&E Engineering Systems. As you notice, the seminar has been a couple of months following the earthquake, so we're looking to have kind of more specific insight into the aftermath of the event. And with that, I'll turn it over to our first speaker, Marty Hudson, who's going to talk on the ground response overview and foundation failure of pile-supported buildings.
Greetings, everyone. This is Marty Hudson from Wood, formerly AMEC Foster Wheeler. And what I'm going to be discussing today is one of the aspects that we encountered as part of the SEAOSC reconnaissance team. So the SEAOSC reconnaissance team was sent down as part of the Safer Cities program, and the team leader was Daniel Zapita from Dig and Cold. We also had Ken Odell, Dion Marriott, Russell McClellan, and Raul Jimenez, as shown on there. We went down a couple of weeks after the earthquake with several different objectives. However, today's presentation, I'm going to only be speaking about one particular structure that we looked at. Nevertheless, before I start, I'm going to give a brief seismological overview, just that will set the ground for this and some of the other presentations. The earthquake that occurred was magnitude 7.1, as shown on the map here. One of the things that was interesting is that the big earthquake for Mexico City was on September 19th, but it was preceded by an even larger earthquake September 7th, but that earthquake was much farther from Mexico City. So although a smaller magnitude, the September 19th earthquake had more damage to Mexico City. Nevertheless, the preceding earthquake had raised everyone's awareness, which helped with some of the response and helped prevent loss of life. Also, interestingly enough, the morning of the September 19th earthquake, they had a drill. And so everyone had just conducted a drill a few hours earlier, which is about the ideal situation. This particular earthquake, if you look at it in cross-section, it's at the confluence of the flat portion of the subducting zone and the portion diving under the plate. And it's at an unusual spot and resulted in this particular earthquake being a normal type earthquake because of its location on the fault. So the behavior isn't what you would typically think of for earthquakes in Mexico City. Here is an illustration out of the New York Times print of where the intensity was measured the most. The darkest red in this figure are the highest intensity, and the light red is the lowest. But what you can see is the typical circular pattern of the intensity around the epicenter, and then you see lower intensity, and then as you get up toward Mexico City, then you get a zone of high intensity again. So Mexico City gets harder than you would expect at that distance. And that is pretty much universally true for earthquakes in Mexico. And that is because Mexico City was built on an old lake bed. So if we zoom in to the lake bed upon which Mexico City is built, you can see the peak ground accelerations estimated by the University UNAM in Mexico City. And so the intensity of acceleration shown here is much higher than you would expect. Similarly, here's the 0.2 second spectral acceleration response and the 1 second period spectral response. One of the things you begin to see in this figure is that there's a band of high intensity that surrounds the city. In other words, the center of the lake bed doesn't have the largest 1 second period spectral acceleration, but rather a ring around the lake bed. Similarly, at 2 seconds, the yellow in this plot is the highest 2 second spectral acceleration, and it's in a fairly narrow ring around Mexico City. If we do a comparison, this is from a computation performed by Guerini and Gazidis of the National Technical University of Athens. They did a numerical evaluation, and if Mexico City is represented as a clay bed with thickening clay, and we have 3 locations shown here, 25, 30, and 40 meters deep of soft clay deposits. And then that is compared to the UNAM rock site over to the side, an outcropping site. Then if you compute the response at these 3 different depths, the response spectra are shown there. And the response is very different. In blue, the outcropping, and then the 25 meter deep spot in red has very high spectral accelerations around 1.2 seconds. At 30 meters, then depth of clay, then the spectral acceleration broadens out to just beyond 1.5 seconds. And similarly for 40 meters, you continue to broaden out the spectral response a little bit. So that's why in the prior graph you have the ring, the band of higher accelerations for some spectral response. It's where you hit a sweet spot of response of the clay deposits. Here's a graph from Greedy and Gazidis showing in yellow where that sweet spot of acceleration lies. And that would be the zone that would impact 5 to 10 story buildings most greatly. So that's where there's 20 to 30 or 35 meters thick of clay. Now, the one building that I'm going to be addressing is shown on this graph as a brown circle there. It is fairly close to that zone of greatest impact. So the subject building we're looking at, I'm going to show in this graph, there's two views. On the left is prior to the earthquake, courtesy of Google Street View. So on the left, you notice the big feature is this ramp from the street up to the parking garage. So there's a large offset elevation-wise between the sidewalk and the entrance to the parking. On the right screen shows that same ramp after the earthquake. And you can see right offhand that there's damage to that ramp. If we do another comparison, looking straight on the left is before the earthquake, and the ramp is easy to see. Then at the right, you can see the building afterwards. Now, first of all, the building didn't collapse completely. You can see that you would expect people to be able to have gotten out of it. But one thing you notice right away is, take a look on the right side where the ramp comes up. You notice that the garage door is now lower with respect to the top of the ramp than it used to be. If we zoom in, and these are both pictures after the earthquake, you can see the top of that ramp and then a step down to the garage. And that step down is approximately 1 foot high. So that indicates that there was relative vertical movement between the ramp on the exterior and the building itself. So the building was down 12 inches approximately relative to the ramp. Here's a view from the other side. On the left is prior to the earthquake. On the right is after the earthquake. Again, you see the ramp as it was built. However, there's the offset, the building being lower than the ramp previously showed it to be. So the structure itself, so you know a little bit more about it, was 6 stories, is 6 stories. And the damage that was observed was both in the infill, and there were in-plane and out-of-plane infill failures. And there was also evidence of non-ductile concrete detailing that had associated damage with it. One of the immediate observations besides the ramp at the front is that the building is now leaning into the adjacent building. You can see that from this photograph, how the gap between the subject building on the right and the red building on the left, the gap decreases as you go up to the top till it looks like the building's resting on the building to the left at the top. The building to the left had very little damage, but this is one of the obvious things, is that we had some tilt of our structure. So then, when we walked up into the structure and looked at the higher levels, then it was, there were some large cracks. This shows one of the cracks widening as you go up to the roof level. And the widening indicates that one portion of the building leaning to the left, the other portion of the building relatively leaning to the right. So that led to that crack developing as shown. As you're walking through the floors, where that crack comes up, it's very easy to see, and obviously to the residents that's a scary sight. But as I mentioned, fortunately, there was not such severe damage that the residents could not get out of the building. Nevertheless, it was a fairly large crack coming all the way up through the building. At the roof level, at the parapet, you see the extreme case of that crack with two portions of the building moving relative to one another. So I've created an illustration which shows the mechanism which would have created this set of circumstances. The Mexico City clay, as I've mentioned before, is famous for how it responds in an earthquake. Not only that, but the clay is not a great foundation support material. And with rock being at depth, one of the choices that you have to support major structures is to put pile foundations extending down to the rock, as shown on the left. So assuming that this particular building, this is how it was originally constructed, the building was placed at ground surface, piles were placed through the clay, extending down to the rock. Then, over time, the clay is continuing to settle, irrespective of any structural forces, and that's due to groundwater withdrawal predominantly from the area, as the groundwater in the lake basin, it continues to be pumped for supply uses. So as that subsidence occurs, then the ground surface around this building would have settled. As that settlement occurs, then you see there developed the need for a ramp to be built to allow cars to get up into the structure and pedestrians. So that's easy to deal with. Every few years, you just come through and you make the ramp a little bit higher. However, at the same time, as the clay settles around the piles, it induces down drag forces onto those piles. So as you can imagine, with the additional load from not only the structure, but from the down drag forces of the clay, then the factor of safety of end bearing of the piles on the rock would be gradually reduced because of the increased demand on those piles. So then when you have the earthquake occur, then the clay would exhibit some cyclic softening, which would further reduce or weaken the strength of the clay, and it can induce a little bit more seismic settlement. Not a large amount, but a little bit more. But my hypothesis that I'm positing here is that the piles were already at a compromised factor of safety. So then with the additional seismic loading from the structure itself, going down onto the piles, plus the cyclic softening of the soil around the piles, and a little bit of additional down drag from any seismic settlement, then that was too much for the piles, and they finally punched down into the rock. With that punching down into the rock, that's a difficult process to control in a manner such that it would be a uniform movement. And so then you saw piles settling with different amounts. So looking back at the photograph on the right, you can see then that the piles finally exhibit some settlement, and that, in a sense, the building is trying to catch up with the settlement that the ground has been experiencing for many years. However, the building still didn't make it down to the level of the original ground surface. But nevertheless, when you have 12 inches of settlement, then it's, as I mentioned, difficult to control and would result in differential movement between pile foundations. So in conclusion, this was a case where we saw downdrag effects upon piles. And so it's something that definitely has to be considered in seismic environments, either due to liquefaction considerations or due to other things that cause downdrag. So those downdrag forces can be catastrophic to a building and must be considered in the design of the structure. And to acknowledge this, I'd like to acknowledge the company, which gave me the time to go down, and then the SEAOSC board, who prepared the funds and accepted the grant for the Safer Cities team to go down and view the damage. So that concludes my talk.
Thank you, Marty, for your presentation. I think in the interest of time, we'll move on to the next presenter. We have Ezra Jampole from Exponent, typical concrete frame building in Mexico City.
Thanks, Gilberto. And thank you to everyone else for attending the EERI webinar. I'm going to discuss some overall trends observed by my reconnaissance team, as well as the behavior and performance of a few specific buildings that are prototypical structures in Mexico City. Hopefully this satisfies everyone's appetite for examining both building-specific data and overall trends observed in the earthquake. I was a member of the Building Damage Survey Team, or BDST, which was a collaboration between EERI and several firms. The team included Debbie Weiser from One Concern, who are in the disaster benevolence business using machine learning to help first responders identify where to focus efforts immediately following an earthquake, Jeff Hunt and me from Exponent, and Maurizio Gabato from RMS. The objective of the BDST was to assess the conditional external damage probabilities in areas of known intensity based on construction type and use, building age, and structural performance factors. We aim to identify the probability of different damage conditions and what factors might influence those probabilities. Naturally, this requires a fairly large data set. We observed the condition of over 700 buildings in Mexico City, primarily in groups close to recording stations. We focused our efforts around recording stations so that we would have a good idea of the intensity of the earthquake for all of our buildings. For an earthquake like Mexico City, where you see similar PGA around the city, we knew that some of the differences would likely lie in alternative intensity measures, including not only spectral acceleration, but also ground motion duration, PGV, incremental ground velocity, cumulative absolute velocity. The list can go on. We only have confidence in the intensity of shaking when we are close to a recording station, so it was crucial that many of our observations were near recording stations. The figure on the left shows a bunch of red dots, each of which indicates a building that we observed. We can zoom in on one of these areas, as shown in the figure on the right, and see that it's actually a number of red dots, each representing a building around a recording station. In this case, we observed every building within approximately 200 meters of this recording station. Here we see a map of Mexico City. I've overlaid a color map indicating the period of the soil. Red and yellow is in the lakebed zone, with long period soils 1.5, 2, up to 4 seconds. Green and the yellowish are in the transition zone, with soil periods up to 1.5 seconds. And the uncolored areas are firm sites. The black dots and corresponding text indicate all of the recording stations that the BDST visited. The damaged areas were primarily in the transition zone, so we weighted our observations more heavily in this area. However, we also visited sites with less reported damage and outside the transition zone to help tie ground motion intensity measure and things like construction type to our damage fragilities. Overall, we visited 13 recording stations. Here we'll compare the geomean horizontal ground motion response spectra from each site we visited to the code design response spectra for 3 major iterations of the governing building codes in Mexico City: 1976, which was before the 1985 earthquake, 1987, and 2004. I'll note that, unlike in the US, the return period earthquake and expected performance is not explicitly defined in the Mexico City building code. We show the spectra by soil zonation, firm, transition, and lakebed zone, and use the CICM definitions for each ground motion station. We can see on the left the codes did not change tremendously from 1976 to 2004 for the firm zone. And the ground motion recording from the station we visited is fairly close to the design spectrum in the short period range, as well as being far below it in periods longer than about 1 second. On the right, we see the Lakebed zone sites. And other than one station in the narrow range of about 1 to 2 seconds, the spectra are typically below those from 1987 and 2004 codes, but above the 76 design spectrum. In the transition zone sites, we see that some of the spectra are significantly greater than the 1987 and 2004 design spectra, especially from 0.75 to 2 seconds. Based on examining the site versus design response spectra, we would expect the majority of damage to occur in the transition zone, with some potentially in the Lakebed zone sites near the transition zone, which is essentially what everyone has observed. We'll also expect damage to be scattered because the individual record spectra are very peaked. On this slide, we show the geomean intensity measures for all the recording stations in Mexico City and highlight the ones that we visited in red. We can visually confirm that the sites we visited represent an assortment of values for different intensity measures: PGA, PGV, incremental ground velocity, the average spectral acceleration from periods 1 to 3 seconds, and cumulative absolute velocity. And we saw that we had an assortment of spectral shapes on the previous slide. Based on this assessment, our database of observed buildings will have a variety of ground motion intensity measure values, which assess in creating damage fragilities. Now that we've discussed the varying ground motion intensity measures, I will explain how we noted observations at each building. We conducted external surveys only, which was partially because we would only have access to the interior of some buildings and partially to save time. We wanted to develop a large data set, and that can take quite a bit of time if you go into every single structure. We noted building age, construction type, use, number of stories, and very importantly, if there are any structural performance factors that might affect the behavior of the structure. We can look at the building pictured below, which exhibited a number of different structural performance factors, for examples of each. On the left, we see the building was irregular in plan, so there might be some torsional effects. This building had multiple vertical irregularities. Note that that wall stops and has to be transferred. The vertical load has to be transferred away. And there's also a soft story in this building, which is another type of vertical irregularity. We can see the short column in the third picture from the left. And there's also pounding potential against the adjacent structure, which is ubiquitous in Mexico City. We categorize buildings by the level of damage: none, minor, moderate, severe, and collapse or partial collapse. We can see a few examples of what falls into each of these categories below. Minor damage is shown on the left. The fascia of the beam has failed and fallen, and we also see some masonry parapet that's been damaged. Moderate structural damage included spalling of concrete on structural members and similar consequence damage. Severe damage included loss of significant masonry in infill frame buildings, and collapse is collapse. Now I'll provide an overview of the damage statistics. The figure on the left shows the number of buildings grouped by damage state and height. We combine light and moderate damage, and we combine severe and collapse damage so that we only have 3 categories we'd really consider: no damage, which isn't pictured here, relatively light damage, and then severe damage. Height bins are in increments of 3 stories, and every building observed over 12 stories is lumped together. You'll note that the lightly damaged buildings were more numerous in shorter buildings, and the more heavily damaged buildings tended to fall between 4 and 9 stories. This is consistent with the expected period of buildings around the ground motion response spectrum peaks. On the right, we see the percentage of buildings in the lump damage state by building type. For example, 90% of the severely damaged and collapsed buildings, which are DS3 and DS4, were reinforced concrete frame buildings with masonry infill, confined or unconfined. A disproportionate number of the severely damaged buildings were of this type, indicating their vulnerability compared to, for example, steel frame building. On this slide, we'll examine the influence of differential structural performance factors and the number of structural performance factors on building performance. On the left, you see the percentage of buildings with each performance factor corresponding to each damage state. For example, nearly 50% of severely damaged DS3 or DS4 buildings had soft stories, and over 90% of severely damaged buildings had pounding potential, though they didn't necessarily have observable pounding damage. On the right, we see the percent of buildings in each damage state that exhibited different numbers of structural performance factors. For example, 100% of severely damaged buildings had at least one structural performance factor that could negatively impact building performance. Notably, 70% of undamaged buildings also had at least one performance factor. It's fairly obvious to point out that more heavily damaged buildings are likely to have additional numbers of structural performance factors. If you're interested in learning more about the overall performance of structures, the BDST report will be released through EERI soon-ish, and the complete data set and metadata will be publicly available as well. Now we'll look at a case study set of buildings that represent a nice cross-section of the typical buildings we observed. Buildings are near the SCT2 recording station, which is in the gray area between transition zone, lakebed zone, kind of in between where that's classified. In the lower left, we see the geomean response spectrum compared to the code spectrum from each year for both the lakebed and transition zones. These structures all appear to be built before the 76 code, so they were likely built just using rules of thumb and not to a particular design spectrum. We can see that the site spectrum is peaked around 1.7 seconds. In the upper right, we see the outlines of the 4 structures that we're going to talk about. And in the lower right, we see a Google Street View image of the corner building at this corner. We'll progressively go through observed damage in the buildings, starting with the damage to the stucco facade and masonry in the building on the corner. Here we see the stucco has fallen off the structure, exposing the concrete frame and masonry infill behind it. There appears to be a couple of pretty short concrete shear walls as well that notably are uncracked and don't appear to be damaged significantly. You can see large X cracks in the masonry in both directions, and an infill wall has fairly obviously completely collapsed, and infill has eliminated from other bays as well. We can go around the corner and see the adjacent building. Notice the large cracks in the concrete columns at multiple levels. These occur at the short columns in the structure, one of our structural performance factors. We'll continue walking down the block and we'll look at the next building in the line, which is a few stories shorter, hence has a lower pier than the first 2 buildings in the row. Here we see some X cracks through the stucco, but very little has spalled and no masonry has fallen into the street. We'll look now at the interfaces between the 4 buildings. If we go back around the corner again, in photo 1, we see that there isn't much damage and there are no signs of interaction between the building on the corner and the shorter adjacent building. In photo 2, we see that the second building in that row, from 2 slides ago, appears to be leaning away from the building on the corner. And in photo 3, we see that that building is in fact leaning onto the shorter end building. On this side, we'll look at the egresses for a few of these buildings. We can see not only bricks fallen near egresses in photo 2, we also see in photo 1 and photo 3 that stairs in orthogonal directions have fractured and separated from the buildings, indicating that there's probably at least a little bit of foundation movement, though we weren't permitted to venture close enough to really perform a detailed investigation on this one. Finally, we'll look at what I'm going to call the orthogonal direction to the primary damage directions we've already observed. We can see masonry infill walls and shear walls, especially in photo 2, that are completely uncracked and undamaged. And I think the lesson to be learned here, tongue-in-cheek at least, is that if you build a structure with no doors and windows, you have a very good chance of surviving an earthquake. To summarize this 4-building L-shaped block, we see that similar buildings have very different degrees of damage. The 2 taller buildings likely have periods closer to the peak of the response spectrum from the recording station close to the site, while the other 2 buildings are shorter away and away from that peak. The potential for pounding is high. The buildings are only separated by 10 centimeters or less. However, it may have actually helped in this case. The middle building was leaning against the shorter end building at the end of the earthquake. In fact, if you numerically model rows of structures, you'll find that in some cases the pounding hurts you significantly compared to no pounding. However, there are cases when the pounding can help prevent collapse by providing confinement to the adjacent buildings. Corner buildings can serve as fuses in these blocks, and they are particularly susceptible to damage. As expected, we saw significant damage in the short columns because they must undergo the deformation of the story over a much shorter length, hence they experience high strains in the local areas. The large openings are not helpful. In the building on the corner, we saw large openings with masonry infill that was not particularly well confined or attached to the frame, and they ultimately failed. Finally, we saw these severed and damaged stairs and fallen bricks near the stairs, showing that it might not have even been safe to evacuate during the earthquake. Before I wrap up, I want to show a new construction site for a concrete frame with confined masonry in an area of Mexico City that did not experience particularly intense shaking. The poster in the front of the building, which you can see blowing in the wind a little bit, indicates that it will open sometime in 2018. We don't know any details of the structural design, like any of their concrete detailing, but we can point out numerous structural performance factors that we know will not be helpful during an earthquake. There are large openings in the street-facing direction, and the poster on the front of the building shows that these will be glass facade upon completion. So it's a little unclear to me if there will be any lateral resistance in the building in that direction, other than the very narrow concrete columns. There's a vertical irregularity. Note the column that ends and has its load transferred to other columns at that second floor. There's a short column hiding behind the truck. And finally, as with almost every structure in Mexico City, there's the potential for pounding against the adjacent shorter structure. It certainly has a different period and can potentially vibrate out of phase with our new building during an earthquake. Hopefully, the lessons learned from this earthquake regarding performance factors will be helpful in preventing future damage. A lot of these are fundamentally architectural issues that are solvable as long as structural engineers identify the problems during design. I'd like to acknowledge the members of my reconnaissance team and several others who assisted with data collection at various points during our reconnaissance trip. Thank you, and if there's time, I'd be happy to take questions.
Thank you, Ezra, for that presentation. We do have one question for you on is the damage observed in the transition zone influenced by the design coefficient below the acceleration produced by the earthquake? Sorry, I'm having that. For those of you asking questions, if you could please know what speaker the questions are intended for. I believe this is for you, Ezra, and I'm actually having quite a bit of trouble following the question myself because I have a very little screen to look at here.
Might be experienced. Yeah, so in the transition zone at the longer periods, the current design codes are obviously not as intense as in the Lakebed zone, primarily motivated by a lot of what we saw in the 1985 earthquake. And since we were seeing higher accelerations in the transitions, higher spectral accelerations in the transition zone in this earthquake, that's something that should be considered for future iterations of the design code, increasing those accelerations.
Yeah. And we also have another question related to, and I don't know if you know this, in regards to building distances between buildings. Are there any requirements in the Mexico Building Code?
I'm not aware of that off the top of my head. I think that EERI's confined masonry network has some guidelines for what they suggest the distances should be, and I think that it's around 10 centimeters for a lot of buildings, but of course that varies with building height as well.
Okay. All right. Okay, thank you, Ezra. We have several questions coming in now, including some from Marty, but I think we'll probably take more of those towards the end of the session. Next, we'll have our third presentation by Prateek Shah from Purdue University, who's going to speak on the building Oaxaca 80.
Thank you, Gilberto. Okay, so today I'll be talking to you about a very interesting case. This is a building made out of reinforced concrete that we surveyed after the 2017 earthquake in Mexico City, and it's called Oaxaca 80. The reason why I think this building is very interesting is because it was built in 1982, and it went through two major ground motions, one in 1985 and one in 2017. Now, this building was extensively studied after the 85 earthquake, and after the 2017 earthquake, we went back to this building and did our own studies. So let me begin by showing you the building. So here's what it looks like. This is an eight-floor building with one basement, and in the direction parallel to the street, and this is the street for your reference, the building has reinforced concrete frame with waffle slabs and beams. And in the direction perpendicular to the street, the building has reinforced concrete frames with waffle slabs and beams and masonry infill walls in all bays. This photograph shows you the layout of the building. Again, what you can observe is that the building has a fairly irregular layout. And as I mentioned before, in the direction parallel to the street, you have reinforced concrete frames with waffle slabs and beams. And in the direction perpendicular to the street, you have reinforced concrete frames with waffle slabs and beams and masonry infill walls, as shown by these lines here. Now, like I mentioned before, this building was surveyed by Dr. Roberto Stark after the 1985 earthquake. And what he found after the earthquake was very interesting. He went to each and every floor of the building and he documented every damage extensively. And what he saw was that there was a small diagonal crack in the second floor column, as shown by this red box over here. And along with the damage to the column, there was quite extensive damage to the masonry, as shown by these yellow boxes over here. What's interesting to note is that there was no damage observed in the direction perpendicular to the street. Now, after the 2017 earthquake, me and some of my colleagues from Purdue University went back to this building and we surveyed it again. This time around, however, we did not go to every floor because we did not have access, but we went to the basement and the first floor. And what we saw was very, very interesting. What we observed this time around was that there was a shear failure in the first floor of the column that suffered a shear crack after the 85 earthquake. Along with the shear failure in this column, we also observed shear cracks in 3 other columns, as shown by these red boxes. This is what it looked like. So the picture on the left shows you the column that had the shear failure, again, quite severe. And the picture on the right shows you the column with some shear cracks and also some bond splitting cracks along the sides. In addition to the column damage, there was also some damage to the masonry. And it was mainly concentrated along these 2 bays over here, as shown by the yellow box. What was interesting to note again was that there was no damage in the direction perpendicular to the street. And this photo just goes to show you what the typical masonry damage looked like after the 2017 earthquake. In the direction parallel to the street, there's quite a lot of damage to the masonry, and in the direction perpendicular to the street, we had a lot of masonry walls, and therefore we did not observe as much damage. Now, what we can clearly conclude after looking at the damage after the 85 and the 17 earthquake is that the levels of damage were quite different. In fact, one could argue that the damage after the 2017 earthquake was a lot more than the damage that we saw after the 85 earthquake. If we look at the demand that was placed on the building, and we do so by looking at the displacement spectra for a linear oscillator with 2% damping, what we have here on the y-axis for the plot is the spectral displacement value in inches, and on the x-axis is the period in seconds. The black line shows you the displacement spectra that was recorded after the 85 earthquake by a ground motion station called SCT. Now, this is a very famous ground motion station in Mexico City, and it was one of the only few stations that picked up the 85 earthquake. The line in blue here shows you the displacement spectra that we calculated from the same ground motion station after the 2017 earthquake. Now, these stations are 3 miles away from the building. After the 2017 earthquake, there was another station 3 blocks away from the building, and the displacement spectra from that building is shown by this red line. We went in and calculated the period of the building, which turned out to be about 1 second. What you can observe here clearly is that the displacement demands, although they were different for each ground motion, they were not off by more than 20%. And this does not make sense because the level of damage that we saw in 85 and in 17 was fairly different, but the demands do not show it. So to make sense of it, we ran some numbers. We used 3 approaches. The first 2 approaches involved running nonlinear dynamic analysis. We used 2 software packages to do so. The first one was LARZ. Now, LARZ is a software that was developed at UIUC in the 1970s, and it uses a lumped plasticity model. We also used OpenSees, and for our OpenSees model, we used a distributed plasticity model. And we also used what I would refer to as a simplified approach, and I'll talk to you more about this later in the presentation. So let me show you some of our results from our analysis. When we used LARZ for the SCT 85 ground motion, we got a roof drift ratio of 4%. And in my presentation, I'm going to use the roof drift ratio as a measure of predicting damage. Now, 4% roof drift ratio would suggest that the damage should have been a lot more than what was observed after the 85 earthquake. So clearly, something isn't right here. After the SCT 17 earthquake, our model said that we would expect a roof drift ratio of 2%. Now this makes a little more sense, but clearly this value is too high if we compare it to the damage that we observed after the 17 earthquake. We ran our model using the Roma 2017 earthquake, and we again got a roof drift ratio that would suggest that the building should have seen more damage than it actually did. If we look at the results that we obtained using our OpenSees model for the 85 earthquake, we got a roof drift ratio of 3%. This would again suggest that the damage that we saw should have been a lot more. So again, the OpenSees model does not make sense. The SCT-17 would have suggested that we would have seen 2% drift ratios at the roof. And again, this would not make sense if we look at the damage that we saw. For the Roma 17 earthquake, however, the numbers start making more sense. At 1%, we would have perhaps seen a little more damage than we actually observed after the 17 earthquake, but it's better than all the other numbers we have up here on the screen. Now, running nonlinear analysis can be time consuming, and it's sometimes very difficult to get right. There are a lot of parameters that you need to play with to get it right. So we tried using a very simple approach so that we could get a consistent result, not just for this building, for other buildings in Mexico City as well. So like I mentioned before, if we go back to our displacement spectra and we calculate our initial period for the building, we get a period of 1 second. Now this building saw quite a bit of damage, and I would think that it's fair to assume that it went into its nonlinear range of response. And if you read some of the work done by Dr. Shimazaki, what you can say is that in the nonlinear range, you can expect as much as 40% increase in the period of your building. And if we use that assumption, we can say that the building of our period, or the period of our building, was 1.4 seconds during the earthquake. Now we have 3 different displacement spectras. We assumed that we could represent all of these 3 displacement spectra using a single line approximation as suggested by Dr. Lepage. And we calculated our roof drift by simply taking the spectral displacement value at a period of 1.4 seconds and projecting it to the roof by using the modal participation factor for the building, which was about 1.3. Now, this approach that I talked to you about is not something that we came up with for this building. It has been used many times before. In fact, in 2016, Lafferty compiled a database of test structures that were tested in lab and structures from the field that were instrumented during strong ground motions, and he made this simple plot. On the y-axis, you have the measured drift that was obtained by instruments, and on the x-axis is the drift that he calculated using the simplified approach that I talked to you about. And what you can see here is that we can see a very good correlation between measured drift and calculated drift. So for our building, if we look at the numbers that we get using a simplified approach, we get the same numbers for all 3 ground motions. And again, this is because we're using a single displacement spectra value for all our ground motions. But the numbers seem to suggest that the damage that we saw was, in fact, probable. So for 0.8%, what you'd expect is some sort of damage in the building, but not as much as what the nonlinear analysis would suggest. So to conclude, all I'd like to say here is that for our building, the simplified approach seems to work. The nonlinear analysis that we ran was time consuming and it was very detailed, but for some reason it did not give us a very good correlation with the damage that we observed. So the simplified approach, at least in this case, seems to work better. Now, all the data that we have for this building, including ground motions and building drawings, are available on datacenterhub.org. And I would like to invite all of you to go onto this website, get the data, look at it, and run your own analysis to see if you can make sense of what happened to this building. Now, to end, I'd like to acknowledge the National Science Foundation and the American Concrete Institute for giving us the opportunity to go to Mexico City and survey buildings. We were able to survey over 130 buildings, and the data for all these buildings will soon be available on Data Center Hub. And with that, if there are any questions, I'd like to take them now. Thank you.
Thank you, Prateek, for an excellent presentation. We do have one question for you. There's a viewer asking if you could share a little bit more details on the numerical models you developed.
I do not have them with me right now, but the numerical models are available on datacenterhub.org. So I guess if they'd like to go there and take a look at them, that's fine. Or they can send me an email, which is also available on the link that I provided. And I'd be happy to talk about my models.
Okay, thank you. We also have one question that came in that I didn't see until now for our first speaker, for Marty Hudson. The question is, do you know what material was used for the piles, and how do you know that the pile, if the pile is punched through the bedrock, or if it was truly touching the bedrock, or was it a failure of the piles themselves?
Yeah, thank you. This is a great question. We did not get enough material to know the precise nature of the piles themselves. So there are a number of presumptions that I am making, and it is possible that the piles themselves structurally failed versus them punching down into the rock. So those are two feasible mechanisms. And as far as the rock, I am also using that term generically to indicate the firmer material at the base of the soft clay material. So there is a lot of unknowns about this particular project at the time, but the basic ideas of what led to the failure are more likely than not.
Okay. Thank you, Marty, and also thank you, Prateek, for answering these questions. We'll move on to our next speaker on the building performance in Mexico City. This will be given by Jennifer Land with Gilsanz Murray Steficek, and also working with the ATC team.
Hi, good morning. This is Jennifer with GMS, and this presentation will focus on ATC's trip to Mexico City and the work we did after the trip. So just an overview of the ATC team. This is a big team composed of practicing engineers as well as professors from different universities. We have people coming from the East Coast, the West Coast, all through the country, and we even had geologists who flew in from Athens to join us on the effort. So it is a truly diverse group. In addition to the ATC team, we received a lot of support from the local engineers, the universities, as well as our local contacts. We received support from WSP's local office, from UNAM, the University of Morelos, the Mexico Society of Structural Engineers, as well as a couple of the practicing engineers who showed us their buildings and gave us information such as geotechnical reports, building drawings, and structural analysis models that, as you will see, allowed us to do a lot of the work that's beyond just reconnaissance. And the mission of the ATC team is to look at buildings that were damaged in the earthquake and the buildings that were not damaged. And the goal is to help two different ATC projects, ATC 78, which is a simplified methodology to look at the collapse risk of different non-ductile concrete buildings funded by FEMA, and ATC 134, which is to look at earthquake damage of concrete buildings with analysis, and that's funded by NIST. So the data we're trying to collect included the type of damages the building suffered during the earthquake, the ground motion the building experienced, as well as dynamic properties of the building. So we were able to monitor the buildings that we had access to see what kind of dynamic information we could collect. We were tasked to look mainly at the concrete buildings, but really once the team went on location, we looked at everything that people found interesting. And just a little bit more about the ATC 78 methodology, because that's the main reason we went to Mexico. It's a way to look at, to categorize the risk of collapse of different buildings, collapse being defined as the global loss of vertical load carrying capacity. The methodology tries to offer some simplified analysis methods by looking at the wall index and the global demand to capacity ratio, but there is a method to do a full analysis, and when that's possible, that is the recommended method. And buildings are categorized into low collapse risk, medium, high, and exceptionally high. And we went to Mexico City roughly 3 weeks after the earthquake. We were there for a week, and we looked at 70 different buildings. Most of these buildings we observed from street level because we couldn't get access into the building. We were able to get into 21 buildings, and we had the time and we had the manpower to monitor 5 different buildings. And this is a map showing the limits of Mexico City and where the collapsed buildings were. And we used this as a guide to the neighborhoods we wanted to visit. And these are the actual sites we visited. As you can see, the green and the blue means the buildings are operational, and the yellow are the buildings that received some damage, and the red and the purple are the buildings that were severely damaged or collapsed. So we had a range of different, we looked at buildings that behaved differently, and we went outside of that zone where the collapsed buildings are because there were buildings we know we could get information on. So we went outside of those neighborhoods too. And today we're going to look at 2 of the buildings that we have the most information on, and we have done a little bit more work since the reconnaissance trip. And conveniently, those buildings are located in the same neighborhood shown on the map. And because they're located close to each other, we got the ground motion from one station that we think is close to both of those buildings. As you can see from the ground motion that, the maximum acceleration experienced in the zone is around 0.4 G, but the 2 buildings we looked at had a building period between 1 to 2 seconds. So we think they saw an acceleration of about 0.3 G. This is the first building. As you can see from the photo, it has severe structural and non-structural damage. If you can see through the windows, you will see that part of the building is short because there was cracking in the slab. And this is a typical floor plan of the building. It is L-shaped. It has a re-entrance corner. It's a very typical construction that we saw in many of the concrete buildings. It has a waffle slab with columns. The region where the slab was has a lot of cracking and it's short up. It's in the lower right-hand side of the slide where the red lines are. And according to the building engineer that we talked to, he thinks that some cracking happened in the 1985 earthquake, and they were not discovered. And in this latest earthquake, the slab was just further weakened. There are 4 walls showing in green in the building, and those walls were not part of the original construction. This building was reinforced after the 1985 earthquake, and the walls were meant to make the building stronger. You see that the engineer who did the retrofit tried very hard to make a core around the center of the building, but because of the layout, the northern wall has to be placed at a different location. And also the walls had to allow openings for people to get into the apartments. So the walls are connected to columns on one side, but had a link beam connecting to the column on the other side. And here are some of the images we took during the trip. We saw cracking on the underside of the slab at the slab to column joint. We saw that part of the building was short all the way up the building because of the cracking in the slab. And another thing we saw in this building that's typical of many of the buildings we went into is that the partition walls in the apartments are unreinforced masonry. And because the building didn't have a whole lot of walls, these unreinforced masonry walls really did a lot during the earthquake to resist the lateral forces, and they suffered a lot of damage. So these walls are generally replaced after the earthquake, but because they were there, they most likely took some demand away from the structural elements. And then here we have some images of the link beams throughout the different levels. At the second floor, we saw there were big cracks in the link beams and some evidence of concrete falling. As we go a couple of floors up, we still saw the cracking in the link beams, but they were hairline cracks. And then at the upper half of the building, we saw that the finishes are still intact, but there are some cracking in the finishes. So the link beams at the lower floors clearly saw a lot more force and a lot more damage. So we looked at this building through the ATC 78 methodology, and we saw that according to ATC 78, this building is a lower to medium risk building, and the risk is associated with the collapse. So that's generally consistent with what we saw in the field, that the building suffered damage, but it didn't collapse. The reason that part of the slabs are near collapse is because we think it's because the building saw the slab saw damage in the previous earthquake, and those damages were not repaired. We got the building analysis model from the building engineer. So our next steps are, we also monitor the building, so we have a set of dynamic properties for the building. So our next steps are to calibrate the dynamic readings we have with the model, and then to use the ground motions we have to see if we can predict the damage this building saw and see what are possible options of reinforcing this building. The second building we're going to look at is a newer building. It's built in the last 10 to 15 years. This building has shear walls and steel columns, so it doesn't quite fit in the ATC 78 methodology, but we think it's interesting enough, so we did more work on this building. This is a typical floor plan of the building. As you can see, it has a lot of walls on the north side of the building where the kitchens, the closets, and the bathrooms are. But on the south side of the building where the living room and bedrooms are, the layout is very open, and that creates a torsional irregularity in the building. The slab is a concrete waffle slab, and the columns are either small steel columns or small concrete columns. We saw again that in the region of the building that's open, people put up their own partitions, and those were mostly URM, and those partition walls saw a lot of damage. And when we went to see this building, it was 3 weeks after earthquake. People were starting to put back their partition walls, and some people started putting back partition walls using light gauge material that has a sliding top connection. We think that may affect how this building behaves in the next earthquake, because the URM walls took so much of the damage during the 2017 earthquake. These are some more photos showing that the small columns saw a lot of damage, and that the URM walls generally all had to be replaced after the earthquake. And then at the connection between the steel column and the slab, we saw some cracking on the underside of the slab, which suggests that there may be incipient punching shear failure. And we think this is important because this is related to the gravity load carrying capacity of the building. So when we came back from the trip, we tried to model the capacity of this connection. We did many different models, from a simplified frame model to a full-blown 3 solid model. And what we saw is pretty consistent in all the models, that the joint has the capacity to accommodate about ½ an inch of movement, which is roughly 0.4% of the story drift. So if the building were to see 2% story drift based on the US design code, this joint would not have worked. And then we looked at this building in the ATC 78 framework, and we saw that ATC again said this is a lower to medium risk building. And we're looking more closely at how ATC deals with the significant irregularity of the building structural system. So that's one of our next steps going forward. And in the meantime, we heard back from the building engineer that this building will be retrofitted and that the flexible portion of the building will see some additional brace frames that will strengthen the building and try to correct this torsional irregularity in the building, and that some of the columns will be strengthened as a result. So we think this will help the building in future earthquakes. So that was a very brief summary of the 2 building case studies that we are still working on. We just want to acknowledge all the help we've received on this trip and in our research efforts after the trip, from ATC, from UNAM, from really a group of people who were more than happy to help us and gave us a lot of information that contributed to our research and the additional work we have going forward. Thank you.
Thank you, Jennifer, for your presentation. I'm trying to look up questions. Can you go over again the retrofit method that was used for the building number 2? What was done to that building, or how were the columns strengthened?
Yeah, so this retrofit was actually done without our input, because while we're doing the analysis, the engineer had to come up with a plan to retrofit the building. So we were working in parallel, but what he told us was that in the floor plan, you can see the highlighted lines in yellow. That's where the additional brace frames will go. Some of the brace frame will be chevrons, as shown in the elevation, and some brace frames, I believe, will be X braces. And because these brace frames will put more load into the columns will be reinforced so that they can take the additional force. And what this retrofit does is, before, all the lateral resistance in the building was on the north side. Now there is some lateral frames on the east and west side of the building, on the south side, and that will correct the torsional irregularity, especially at on the south side of the building, where there's not a lot of lateral resistance in the beginning.
Okay, thank you. So thank you, Jennifer. Let's move on to our next presentation by Mark Yashinsky from Caltrans, speaking on the performance of bridges.
Hi, so I'm Mark Yashinsky. I work for Caltrans. I'm a bridge engineer, and I was part of the advanced gear team that went to Mexico City. Gear is usually about the first team that goes out after an earthquake, and we arrived 5 days after the September 19th Mexico City earthquake. And our team leader was Kevin Franke, and we partnered with the National Autonomous University of Mexico, and their dean was Juan Merrill, who was very helpful during the investigation. Oh, that's me above them. And we were the advanced team, but we were followed by the main team immediately after we left after a week, which was led by Tara Hutchinson at UCSD. Anyway, most of these people are geotechs, and I'm a bridge engineer, so during most of our investigation, I was always begging them if we could stop and look at a bridge. So just a little bit of information to start. In Mexico, about 70% of the bridges were constructed before 1970, before they had any kind of seismic design criteria. And there's been no bridge retrofit program since then to address the vulnerabilities of these bridges. New bridges are typically designed using the AASHTO bridge design specifications, which is the same specs most of the states use. And that includes some seismic design criteria. Bridges also have to comply with some local seismic codes, like in Mexico City, which can be more intense than just the AASHTO code. Most bridges perform pretty well. However, I think they were generally lucky because the ground shaking was low, and we noticed that it seemed like the construction inspection was often lacking. And of course, this existing inventory was mostly designed without seismic design. So, however, you know, it's very, very expensive to do a retrofit program. And in California, it's cost us many billions of dollars to retro our bridges, and maybe it's not really justified. So it's, I guess it's a probabilistic and economic decision everybody has to make. At any rate, in California, just like in Mexico City, we built most of our highways before 1970 with minimal seismic design. However, in our case, we had several retrofit programs after 1970 where we try to address different vulnerabilities as we learn more things about the earthquakes. And of course, all our new bridges are designed using our own seismic design criteria. Anyway, these designs usually include continuity, which carries the loads for vulnerable elements to much stronger connections, and also to provide ductility to allow fuses to protect the structure. And also we try to provide balance between parallel elements to prevent the force to going into the stiffer elements and causing damage. And also we try to design our structure to have a period where the forces won't be too great. And Caltrans' philosophy is basically to allow damage to the ductile members to protect the bridges from collapse. So we've talked before about how most of the damage occurred in the transition zones at the edges of the lakebed. And you can see this is a map, a Google Earth map that shows the 1 second spectral acceleration. And bridge engineers, we usually pick the 1 second spectral acceleration because we typically try to design our bridges for about 1 second period. Longer bridges have 1 second or greater, shorter bridges probably have a little less. And so you can see that the 1 second spectral acceleration over here in the transition zone was about 0.24 G. And so most of the bridge damage we saw in Mexico City was in that ground shaking of about greater than 0.25 G, 24 G. Then we also saw a couple bridges in the state of Morelos, and that was more due to lower shaking, but also weaker soils. And finally, we saw one bridge damaged in Puebla State, close to the epicenter. So the first bridge we looked at was a pedestrian overcrossing in Mexico City. This pedestrian overcrossing had poor continuity and came apart at the connections. And so you can see the bridge before the earthquake. Then after the earthquake, it came apart at the connections, unfortunately falling onto a taxi. The second bridge we looked at was a long metro train viaduct. These viaducts are very popular in Mexico City because you can just put them on single column vents in the median of a road or a highway or an expressway, and all of a sudden you have much greater capacity. This viaduct suffered medium to severe damage during the earthquake. So on the east end of the structure, we saw several vents that rocked back and forth during the earthquake, and we generally consider that to be good behavior because rocking protects the substructure from damage. Also, we saw a lot of damage at the superstructure. In this case, the cross bracing had shear keys that went into the bent cap, the concrete bent cap, which moved enough during the earthquake to knock out the concrete. Like I said, that's generally considered good behavior because it doesn't cause any loss of capacity of the bridge. Also, you might notice that these columns have a slot in them, and this slot was probably meant to hold drainage pipes, but we noticed that a lot of times there was poor construction inspection, so these final touches to the bridge like drainage sometimes weren't completed. So then walking along the bridge, we noticed that there was enough shaking to cause spalling of the bent cap as these simply supported spans knocked into the bent cap. And finally, about a quarter mile from the beginning of the damage, we came to some severe damage. They had to go and build shoring column after the earthquake because it was so damaged. And so when we looked at the column, we were surprised to see that the cover concrete had spalled off, and it showed that typically this is the plastic hinge zone, and it's supposed to have very good transverse reinforcement to hold the main reinforcement in place, but it didn't look like there was much transverse reinforcement in the plastic hinge zone. And also they were using couplers for the main reinforcement, which typically we don't do because this main reinforcement is supposed to yield to form the plastic hinge, but if you have couplers in them, they'll fail before they yield. And you can see that core concrete was torn up during the earthquake, and so they thought it was expedient to build some shoring to protect the bridge. And so this bridge had some pretty severe damage due to lack of ductility of the columns, maybe due to poor construction inspection before while this bridge was being built. Then the third bridge that we came to was a 5-span, well, it's a pair of 5-span overcrossings, pier walls with drop bent caps and masonry abutments. And so, like we've seen before, pier walls were very strong, and so they rocked during the earthquake. So the foundation rocked, and then the masonry, unreinforced masonry abutments, the superstructure banged against the shear keys and caused a lot of spalling. Fortunately, not enough to cause any serious damage. And you can see that the bridge is a 5-span bridge with a very long, heavy main span, which overloaded these very small substructures, but fortunately not enough to cause serious damage. Then the next bridge we looked at was the viaduct Tlalpan. Like I mentioned, these viaducts are very popular in Mexico City because they usually provide a toll road for people in a hurry to get it through the city, and they increase the capacity on these highways just by building these columns in the median. And so we stopped and talked to the highway patrol and asked them if they found any damage on these bridges, and they said no, the viaduct was thoroughly inspected and no damage was found. However, they did say that after the earthquake, they found a lot of water draining out of the expansion joints and weep holes on the structure. And so I assumed that what happened was that probably a lot of debris accumulated inside the drainage of this viaduct. You can see again that there was no drainage pipe put over here. And so during the earthquake, a lot of the debris that had accumulated probably got shaken loose and allowed the water to finally drain off the viaduct. The next structure we saw was a pedestrian overcrossing, the Avenue Tlalpan. And this was right next to where a pedestrian, or where an apartment building collapsed during the earthquake, and a tent city had been built. And so this pedestrian overcrossing had been damaged during the earthquake, but fortunately was immediately repaired, which was good since it was heavily used by all the people that needed it after the earthquake. And so we inspected it, but we couldn't find any damage. We just saw the sign saying that it had been damaged. Then the sixth structure I want to talk about were these pedestrian walkways that seem very common in Mexico City to connect structures together. So you can see here there's a parking structure and then a pedestrian walkway that takes you to a Sears store. And these buildings have different periods and move out of phase together. And unless these connections are designed very well, they get damaged during the earthquake. And so in this case, it isn't too bad. People just can't use this pedestrian walkway after the earthquake. But we saw much worse damage at the Monterrey Institute of Technology in Mexico City. And so you can see that the buildings were very damaged. And they also provided bridges between all the buildings, between the floors. And so in this case, the bridges weren't damaged, but behind the buildings, there were some bridges that collapsed during the earthquake, which unfortunately killed 5 students and injured about 20 students. And so when we arrived 6 days afterwards, the students were putting up all these memorials to the victims of the earthquake. Continuity is so important, and also designing, or if the structures are unbalanced, then you have to design the connections particularly well to prevent collapse. Okay, now we're going to leave Mexico City and look at some structures that were damaged in the state of Morelos. The first bridge we're going to look at is Puente Geotepec, 1-span river crossing. Now, the shaking was smaller in the state of Morelos, probably like 0.1, 1 second spectral acceleration of 0.15 G, which, engineered structures like bridges shouldn't be affected by this low ground shaking. However, the state of Morelos had weaker soil. In this case, it was loosely consolidated silt. And so the silt allowed the 2 abutments to move back and forth during the earthquake, which allowed the 1-span superstructure to move off the abutment seats and collapse during the earthquake. Similarly, the nearby Puente Taycuman, the superstructure remained in place, but the embankment had a lot of damage during the earthquake. And what happened was the unreinforced masonry wing walls fell down during the earthquake, allowing the embankment to come down. So no one could go on the bridge because there was no more embankments. And in fact, and then gear team arrived a week later, the bridge had already been removed. Another bridge on the way to Mexico City and Morelos State, a tall 3-span high girder bridge, didn't really suffer any damage, but you can see this is in a high cut area, and the cut around one of the piers sloughed off during the earthquake. Now, the final bridge we looked at, similar to this bridge in Puebla State, this is close to the epicenter, and it was in the town of San Juan Pequillo, which was mostly adobe construction that had a lot of damage during the earthquake. And so this bridge, which was similar to the last bridge we looked at, it was closed after the earthquake. What happened was the connection between the columns and the slab superstructure came apart during the earthquake. And so for safety's sake, they closed the bridge. So this is another case where, continuity is needed between the substructure and superstructure to prevent damage. So that's all the bridge damage that I was able to find during the earthquake. Like I mentioned, most of the damage was either due to lack of continuity between members or a lack of confinement due to poor detailing or the use of unengineered material like unreinforced masonry, and also due to lack of balance, such as between buildings that supported bridges. I'd like to acknowledge John Bray, who selected me to be part of the GEAR team. I want to thank my boss, Mark Mahan, who allowed me to take time off to work to investigate the earthquake. And I want to thank Omar and Maggie, who asked me to give my talk. Thank you very much.
Thank you, Mark, for the very informative presentation. I think questions have been a little bit delayed in coming in, so we're going to move on to the next presentation and hopefully get to more questions at the end of this next and last presentation by John Eidinger from Genie Engineering Systems, and he will speak on the topic of impact to water and power.
Good morning, everybody. Can you see the screen?
There we go.
Okay, great. So I'm going to talk about the impact of the earthquake to the electric system and the water system. And I'd like to thank the many people involved with this, including Alexis Kwasinski from Pittsburgh, Alex Tang, Bruce Mason, Haijong from Oregon. And there's a report for all this called TCLE number 3 available at our website. Also in Mexico, we have to get great support from CFE, which is the name of the electric utility that we're going to be talking about, as well as the water utilities, Conagua, SACMEX, and the CAEM, and several professors and engineers in Mexico. And finally, I'd like to thank Mike O'Rourke, who helped this and has been involved with this since 1985 earthquake. So the key points here to highlight here is the water system in Mexico City suffered about 1,500 pipe repairs. A lot of this was to small diameter pipe, but most importantly, talking about aqueducts. And we find that a lot of the damage due to the aqueducts is due to what are called geophysical basin effects. And we'll talk about that here a little bit later on. Of course, there's no seismic design done that we could observe in the water system. For the electric power system in the September 19 earthquake, 37 different substations suffered damage. Net result was about 5 million people losing power. With regards to what this means to utilities in the United States or California, we have a design standard called ALA 2005. If these were followed, this will solve the seismic issues for pipes. And it's available from the American Lifelines Alliance. For the electric system, there's an IEEE 693 document currently being updated 2018, and will solve most of the damage that we are going to observe, and that's available from IEEE. In terms of California, to get all this done, we still have 50 years of work ahead of us for the water system, and on the electric system, possibly 10 years. The electric system is generally well advanced from where we are in the water systems in terms of earthquake issues. Okay, CFE is the Commission. Most of the power system is run in Mexico is by CFE. The transmission system voltages are 400,000 volts or 230, and we'll talk about what happened there. The next slide shows the electric grid for all of Mexico and highlights the earthquakes of interest here, the Puebla earthquake in 2017 in the red star. Not to forget the Laguna Salada earthquake of magnitude 7.1 in 2010. It had a lot of damage. Chiapas earthquake of earlier in September, and of course prior earthquakes. The utility is well aware that earthquakes occur, and they do take some seismic practices only though along the Pacific Ocean, where the seismic risk is higher, and we'll see that as we go along here. So in the September 7 earthquake, the level of shaking along the ocean, the substations was on the order of half a G strong shaking. They did some seismic design for newer equipment at these substations. However, there was a lot of damage to older equipment, which had not been seismically retrofitted. And the net result was about 126 million pesos worth of damage at those substations. The Puebla earthquake is far more interesting because it affects a much larger population. It's an intraplate event, about 100 kilometers southeast of Mexico City. 37 substations had damage. 6 transmission lattice towers had damage. Buried cable had damage. And most of the substations, all the substations had pretty low levels of shaking, 0.08 G to 0.25 G shaking. So the peak power outages were about 4.8 million people. About a third of all the CFE customers' power lost power initially. By the 23rd of September, 4 days after earthquake, 99% are restored. This did not come without a big effort. Over 3,000 people were involved in the restoration effort. But what are the causes of the damage and what can be done about it? We're going to talk about that next. So the next slide shows the transmission grid around Mexico. And you don't see Mexico City here, but I put a little pentagon which says 22 is 22 million people in Mexico City and is surrounded by 9 blue substations. Those are the 400 kV substations that surround Mexico City. Puebla is where it says 3 million people. The epicenter is shown the red star. And the substations which suffered the most major damage of these voltages are shown with heavy red circles around them. And we're going to talk about substation YTP, which had the bulk of the damage, or the most bulk of it, the large damage. This is an aerial photograph of YTP. It's a 400 kV yard. If you see this, this is a large substation, as are many in Mexico City, around the Mexico area. So this is a very large yard. The level of shaking here using shake maps. Of course, much of this is not based upon instrumental data. It's based upon did you feel it? So it's basically an inversion of Mercalli intensity. The YTP substation here is located around 0.15 G shaking, not real strong shaking, maybe 0.2 G. However, there's lots of uncertainty and there's no instrument at the site. So we have to say it's plus or minus 50%. For those electrical engineers on this little webinar, this will be a one-line diagram of the substation showing circuit breakers in squares and power transformers as sort of zigzags. Everything with a big red square around it. Big red square shows it collapsed in the earthquake, and we're going to go through why that happened. There are 11 transformers. These are multi-million-dollar boxes, transformers. They're all unanchored, not a good practice in seismic areas. They all slid a various amount, and here we show one sliding a couple inches side to side, another one sliding 7 inches side to side. When transformers slide, is wires attached to them. Don't like it. Here we are, the control cables going into one of the transformers. This is, I would not call this a well-designed situation here. And you can see the distortion on the cables. These are what the transformers look like. We had one broken 400 kV surge arrestor and one broken 400 kV bushing. These are what bushings look like. When they break, we're out of business. Fortunately, there was an extra transformer here, so they were able to rewire the transformers, 3 remaining ones, to make a circuit, which is one reason the power outages were not very long. However, this is in the boneyard of broken debris for broken aspects. On the left is the bushing, the broken bushing. But particularly of interest here, I'm just highlighting here this little small bushing that has a low voltage bushing. And when you see this type of damage, you know that unanchored transformers are no good. Again, coming back to the 400 kV bushing, this is a bushing that failed. And we can see the broken porcelain here, not a good seismic design. It's well recognized. The low voltage bushings here, which are attached to the bus work, we're using rigid bus. When these transformers move side to side 5 inches or 7 inches, you are occasionally going to break the bus work or you break the bushing. Either way, you have an outage. Not a good design. Here we're showing electrical standoffs, a long known problem with surge arrestors. This is likely what happened in surge arrestor that failed at 400 kV. This is what the yard looks like. The green box shows pentagraph switches, and they all failed during the earthquake. These are very poor designs. and they cannot take differential movements from the top to the bottom, and they end up in the boneyard, and we have an outage caused by this. These are the replacement, I'll call them candlestick circuit breakers. These are 230 kVs. 3 out of 6 of them collapsed. Again, we don't consider this to be a particularly good design, and you'll see the issues here. No slack in the cables. Not a good seismic design. In the newer part of the yard, there were 12 circuit breakers. They all work fine. However, we go to the boneyard, there's a lot of damage at the yard, and we inspect damage. We start seeing things like this. This is on a circuit breaker which was quote unquote seismically qualified for PGA equals 0.2 G. And we can see that the fact it's in the boneyard here, broken, suggests that the qualification wasn't quite up to snuff. Is much damage in the yard, surge arresters, wave traps. These are current transformers. The dark ones, they're sort of dark brown, are the older versions, and the light sort of gray is the newer ones. Seems to have no impact in terms of old design and new design. They all end up in the yard, in the boneyard. Is the reason that they failed here is I've got to take measures showing, and my arrow is highlighting a cast aluminum fitting here, which is snapped off in the earthquake. This is due to limited slack that we highlighted before. As the components move differentially, they impart big snapping forces when the cables get tight, and this just snaps off aluminum. Those who think that aluminum is ductile, it is not ductile when developed like this. Here is another situation before the damage. Here showing a little angle that attaches the wires. This is undamaged, but this is another similar unit that is damaged. You can see the cast aluminum fitting here is broken off. And here's my hand replacing the part that's broken off. So this is caused by snapping forces due to cable snapping forces. If we follow IEEE 693 or 1527, we take care of the problem, no issue. Is these newer circuit breakers did not fail, 12 of them. So we say inertially they're pretty good for 0.15 G or so. However, this is the yard here that had a lot of damage, and every arrow here shows, this is a photo taken about a month after earthquake, after replacements have been in place. All the units here, all the circuit breakers where the arrows are highlighting, they all collapsed. That's half the yard then went. These are the seismically qualified 0.2 G breakers that are still standing in service. However, some did not quite make it, as we've seen here. This is the control building. It's a non-ductile concrete frame building with little stiff short columns. Everybody would recognize they're not good seismic design. However, 0.15 G at the site, we could not see a scratch to the building itself. So the building was fine, probably because it was low level of shaking. The battery room here, these are station batteries. One of the battery units here collapsed. The rest of them were removed afterwards. It is, I would say, shocking to see a battery rack with no seismic design details in this day and age. And this is unfortunate, but this is what causes power outages, and it would say that CFE has not taken good care of seismic design detailing for these kind of issues, at least near Mexico City, where only 25 million people live. Although the seismic hazard there is pretty small, the cost to mitigate this is next to nothing and should be done. So let's talk a little bit about the water system. And I would call Mexico City, in terms of the entire world, the king of broken, segmented, large diameter concrete pipes. These are our large diameter concrete pipes. We have a lot of them in California. They can fail, and they do fail in earthquakes, and this is an issue. It's certainly an issue in Mexico City, and it is an issue in California. Mexico City is no stranger to earthquakes, and there's been a lot of earthquakes in Mexico City and lots of damage to the water system in Mexico City. In this particular earthquake on September 19th, we had about 1,500 leaks in the system. And I want to highlight, first off, what happened to a 48-inch diameter concrete segmented pipe. It suffered 26 leaks. I would say many of these leaks were, like I would call them, failures over a length of 22 kilometers. And the question is, why did this aqueduct have all this damage? And the answer was, it is not related to permanent ground deformations. It is related to permanent ground or peak ground velocities, but mostly due to basin effects. And I'm going to talk a little bit about that. Mike O'Rourke, Tom O'Rourke, and others in the water business, seismic design issues have a lot of debate on this topic. And this earthquake pretty much settles it, that basin effects are very important when they occur. In our design code, that's the ALA 2005, we recommend design of the joints of 7 times ground velocity V divided by wave propagation speed C, and not V upon C. We use 7 because we recognize there's uncertainties in the joint stiffnesses, and the joints can't just open up 1/16 of an inch. It's going to open up more. However, we now see that the 7 might need to be increased when we have ground velocities which are substantial, or when we have basin effects, or so this is an important issue which is being debated now, and we'll have, I would say, in the next 3 years, an update to the code. Bottom line, V upon C design rule should never be used for design of segmented pipe. You have to put either a 7 or a 10 or a 15 in front to accommodate the uncertainties we have in ground motions. So some photos here of broken large diameter pipes. Clearly, they're big diameter, and when they leak, they're cause a lot of issues. And these pipes don't look any different in many ways to some of the pipes we have here in California. And the repair efforts are substantial and they time-consuming to do. If you have too much damage, they say throw away the pipe and build a new one, which is what we're showing in here. And occasionally they'll use some pieces of steel. So this is very common design. We'll see it in California, we see it in Mexico. The question is, why did we have 22 failures over 26 kilometers? Well, we went back and tried to look at how these pipes were originally designed, and it looks like it's the so-called lock joint pipe circa 1900 design. And this is the design detail of that type of pipe. If we zoom in here at the joinery, we see a gasket, 2 pieces of pipe are pushed together and the gasket sits. And it has about a joint capacity of about 1 inch opening before it opens up and starts to leak. So what causes the joints to open up, or worse, when they open up, they come back together and they pound and we swallow the concrete, and then we have a huge problem in terms of a leak that's not repairable easily. These are the kinds of pipes when they're being constructed. So why do these segmented pipes break? Well, historically, we assume vertically propagating shear waves, but we're now clear that in Mexico City and in basins in California, surface waves or Rayleigh waves may rule and may cause more damage. Basin waves or surface waves are slow moving. We are recognizing that they occur. They're caused by pulses and earthquake, their activity issues, and basin effects. And including in California, we have basins called Los Angeles and Pasadena, and other basins like San Jose between mountain ranges. When the high velocity shaking hits the mountains, they bounce off as slow moving surface waves, and these slow moving surface waves are going to damage segmented pipe. Here's a structural nonlinear model. We looked at this. If we assume case A of a pipeline, here we have a pipe that's about 12,000 feet long. We assume a vertically propagating shear waves, which has been historically, and we find that we project that the joint should open 0 inches, and the pipe moment is 1,260 kip inches, which is trivial for these type of pipes. But case B, if we have one single cracked joint in this whole pipe, run the same earthquake, but assume it comes in as a R wave, then the pipe moment increases somewhat. The joint forces go to 2,000 kips, which is enough to crush the joint when it comes back together again from spalling. And the joint opening here is 1.35 inches, which is enough to cause leakage because these joints are only good for about 1 inch. So clearly, the type of wave, S versus R, is the key. And this is a time history showing the joint movement of that R wave assumption, where the joint peaks open at 1.35 inches during time 15 seconds into the earthquake. At the end of the earthquake, we would see about a 1/4 inch offset at the joint, but during the earthquake, it moves more. Case B, if we if we increase the surface, the wave propagation speed to 10 or 20,000 feet per second, the joint openings drop dramatically, in which case, no real problem. So observations is the joints will open on these concrete segmented pipes, including all our PCCP pipes in California. If we have a single pre-cracked joint, Secondly is they'll open up if there's slow moving traveling waves. These are going to occur if we are in basins. Third, they're going to joint will open up if there's a major stiffness change, like an elbow or a vault. So the bottom line is basin effects, pulses, directivity are all make this a much worse situation. What to do about this for big pipes? First, don't use segmented concrete pipe for critical pipelines. It solves the problem. Second, use chain ductile iron pipe like Kubota or US pipe. That solves the problem. Third, use continuous pipe like welded steel or high density polyethylene. That solves the issue. Or fourth, use long throw joints, which has been done occasionally, but not often in California. All these ways are approaches to solve the problem. With respect to the distribution system in Mexico City, the level of shaking varied in Mexico City, as the prior presentations highlighted. Is the shaking was in the transition in the lake zones much stronger than in the rock or the hilly zones. There's about 20,000 kilometers, not 20 kilometers, 20,000 kilometers of pipe in Mexico City. There were very few permanent ground deformation zones, a handful throughout the city. And if we use the ALA models, what we find out is we forecast 1,185 pipe repairs. The actual is 1,500. The fact is that Mexico City has a lot of subsidence, and this may have pre-cracked a lot of these pipes, and maybe one reason that we are getting a little bit low on our estimates. So bottom line is, as a first order estimate, the ALA models are pretty good, 1,185 versus 1,500, or we can adjust them for Mexico City with a factor K of 1.27 to reflect the special situation in Mexico City with the long-term subsidence issues. So at this point, I thank you very much for your attention. Any questions?
Thank you, John, for your presentation. So let me go back first to a question from Mark, and I'm trying to get through these questions as they come in. And the question for Mark, this is a previous presentation on bridges. Did you see any bridges with stocky or tall, slender rocker bearings, specifically those that may be similar to those used in the East Coast in the 60s and 70s?
No, mostly elastomeric pads. These bridges are fairly simple and straightforward. There might be some bigger bridges with rocker bearings, but I didn't come across them, during our investigation.
Okay, and Maggie, feel free to fill me in with any questions.
Yeah, Gilberto,
and
I'll just go ahead and read this one. This is coming in, and it's a question for everybody. It says, based on recorded motions, vertical to horizontal spectral ratios appear to be much higher than the past major earthquakes. In other words, vertical motions were much more intense than the other previous events in the region. Have you seen a study to understand why this particular event had high vertical shaking and seen apparent damages related to this intense vertical shaking? So I think if any of the speakers wants to jump in to start off.
A quick answer is no, I haven't seen a study of that.
Yeah, I haven't really seen any data on that myself either. We do have one more question for John Eidinger, and that is, did you see any overturning failures of electric or mechanical equipment in both water and electric systems?
John Eidinger, I did see, and I think I mentioned in the slideshow about overturned batteries that were unanchored at one of the substations, and there were other overturned equipment at various spots in the water system and at other substations. Generally speaking, there was not a lot of attention to anchoring down electrical or mechanical equipment in these systems, in part because the level of shaking in Mexico City, if you look at all the design codes, are on the order of 0.1 G. It's not considered to be very strong. And there was just not a lot of attention to these type of issues. Clearly, the intra-slab events, which do occur south of Mexico City regularly, will produce stronger shaking of 0.10 G. So it would be good if the utilities went about their business and did an anchorage effort for their facilities. It would not cost a lot, and it would certainly solve a lot of problems.
Thank you, John. And we have another question. I don't know if Jennifer is still on the line. I'm not sure if she was able to stay till the end, but
Yes, I'm still here.
okay. And what is the question for Jennifer, Maggie?
So this is the question. I believe Jennifer mentioned that they were installing light gauge metal with sliding connections in the partitions. Is this technique gaining in popularity in Mexico or in the US?
In the US, I believe it is the standard. In Mexico, the buildings we looked at, it was not the standard practice. Most of the partitions were URM, but when we went to look at some of the repairs that are being done, some of the partitions, some of the apartment owners are switching to light gauge because they were told that it would behave better and it would suffer less damage in the earthquake. So we're starting to see that, but a lot of the older construction we've seen, they're still all using URM partitions.
There was also another question from Jennifer on whether there was any publications on the results from your presentation.
Right now, we haven't published anything. It's still an ongoing effort to collaborate with ATC, but hopefully we will be publishing some things in conjunction with ATC and the local engineers we are working with in the next year.
I do not see any more questions.
Yeah, I think that's it, Gilberto.
That being said, I want to make, I guess, a couple of announcements and acknowledgements as we wrap up the session. First of all, I wanted just to reiterate that we saw presentations mainly focusing on damage to buildings and infrastructure throughout the city. This was a design level event, and so damage was to be expected. But there are also a lot of success stories throughout Mexico as well. I wanted to thank the speakers for their very insightful presentations, and building upon the webinar we had back in November, going into a lot more detail on observations following the earthquake. I wanted to thank all the participants for joining us online, and hopefully you found this webinar as valuable as I did. I also want to thank EERI, especially Lucia Ren, who's been working with me on co-leading the reconnaissance efforts on behalf of EERI. And special thanks especially to Maggie and Omar for arranging a lot of the details of this event. I want to remind all the viewers that publications related to this and other earthquakes are available on the Learning from Earthquakes website at EERI. And this webinar as well will be posted on there for later viewing. So that being said, I think we're approaching the end of our 2-hour segment. Again, I want to thank all the speakers again for their excellent presentations. Thank you to all the participants for joining us. And again, if you have questions, feel free to contact myself or the speakers, and look at the Learning from Earthquakes webinar for more information on this and other past events. And thank you again to EERI for hosting this event and providing this very valuable information from this and all other past earthquakes through their Learning from Earthquake program. Thank you all.